Hw10 Question 2. In this question, they're asking us about a titration, and they tell us we have a certain volume and molarity of hydrochloric acid, and it's going to react with different molarities of different types of strong bases in parts A, B, and C. Let's start with part A. We have sodium hydroxide reacting with hydrochloric acid, and let's start with a nice balanced equation. As with any titration problem, we'll make water and a salt. In this case, the ions left over are sodium and chloride ion. And let's keep track of the volume and the molarity of the acid. So 28 milliliters of 0.2 molar. If we just multiply volume times molarity, we'll get 5.6 millimoles, or thousandths of a mole. Notice that the equation is balanced as written. Coefficients of 1 will do the trick. So if we have 5.6 millimoles of the acid, how much base is needed? Well, let's use our balanced the coefficients from the balanced equation in order to figure that out. It's a 1-to-1 molar ratio, so the same number of moles of base is required, 5.6 millimoles. In the problem in part A, they tell us that the concentration of that base is 0.1 molar. And we know that molarity is calculated by taking the number of moles of solute divided by the number of liters of solution. Well, that same ratio can be maintained if we consider the number of millimoles of solute per milliliter of solution. It's just a little shortcut that we can use to make this go a little faster. In part A, they said that the molarity was 0.1 molar, and we'll set that equal to the number of millimoles that we had solved, 5.6. over some unknown volume in milliliters. And if you divide that out, we get 56 milliliters for part A. On to part B. B is interesting because we have a base that has 2 hydroxide ions, and that's going to affect how we can balance the equation. We write good formulas for the water and the salt, and then, as you can see, we require a coefficient 2 in front of hydrochloric acid in order to make everything balance. We'd also need a coefficient 2 in front of the water to make things balance. And just like before, when we calculated in part A, we took the volume times the molarity of hydrochloric acid and arrived at 5.6 millimoles of hydrochloric. Well, that same number applies. We're going to do the same thing as before, only this time note that the ratio of coefficients between the reactants is a 2-to-1 ratio. That is, 2 moles of hydrochloric react along with 1 mole of the other reactant, barium hydroxide. That gives us a different number of millimoles required. 2.8 in this case, millimoles of barium hydroxide are required to react along with 5.6 millimoles of hydrochloric acid. But just like before, we'll use the molarity formula and the shortcut that the number of millimoles of solute per milliliter of solution will give you the molarity. In this case, the stated molarity is 0.05. And as we had said before, 2.8 millimoles over some unknown volume in milliliters, X. Well, to get X alone, we would just take 2.8, divide that by 0.05. And in this case, it works out to be, coincidentally, the same volume as we saw in part A, 56 milliliters. On to part C. Part C is just like part A. We have a base with one hydroxide ion reacting with hydrochloric acid. The salt in this case is potassium chloride, but that's not very important. And just like before, we have the same number of millimoles of the acid. In parts A, B, and C, the number of milliliters and the molarity of the hydrochloric acid has not changed, which means that the number of millimoles that you get won't change either. It's a 1-to-1 molar ratio between hydrochloric acid and potassium hydroxide. And so we have a required 5.6 millimoles of potassium hydroxide to make this reaction go. And the last part, once again, use the molarity formula, and we'll use the shortcut that millimoles over milliliters is the same ratio as moles over liters. They give us, in this case, a molarity of 0.25, and we'll set that equal to 5.6 millimoles divided by some unknown volume in milliliters. To get X, 5.6 divided by 0.25, and it works out to be 22.4 milliliters.